We are now going to look at probability, and we're going to look at just basically how it's defined and some of the real simple rules that you can use to help you find probabilities. So probability plays an important role in statistics here. To see that, I got to spell this. I can't do two things at once, probability. So to see why it plays such an important role, just think about the probability problems that maybe you have done before. Maybe you've had a problem where you're told that there's 10 marbles in a jar, 3 of those marbles are white, and the other 7 are black, and you want to know what's the probability of reaching into the jar and pulling out a white marble. And that would be like 3 out of 10. So there's like a 30% chance of pulling out a white marble. So in statistics, we often use samples to represent the entire population. And the samples aren't going to be a perfect representation of the population. So for example, the mean of your sample won't exactly equal the mean of the entire population, but you expect it to be a good representation, an estimate of it. And there's going to be some sampling error. Okay, well, just like you pull the marble out of the jar, when you pull a sample out, you're randomly selecting people from the population. It's a similar situation. The only difference now is instead of just selecting one marble, you're maybe randomly selecting 50 different people. And as it turns out, the error that you would expect to get in your sample, the sampling error, actually is governed by the rules of probability. And so that's why we study probability when we do statistics. So now to define probability, let me just define a few things. So first, an experiment. So in probability, an experiment is not like an experimental study or even a science experiment or anything. Experiment is just the name we use for any action whose outcome cannot be predicted with certainty. Okay, so pretty much any action whose outcome can't be predicted with certainty. So some examples might be rolling a 6-sided dice. Right? You can't predict with any certainty what number is going to come up. Okay, so we would say that's a probability experiment. Another one might be randomly selecting a card from a deck of 52 cards. Okay, again, if you randomly select a card, you can't predict with any certainty what card you're going to select. Now, these two are very common when you first learn probability, because these are situations that we're somewhat familiar with, rolling the dice or selecting a card from a deck, because we all play, games that involve rolling dice or playing cards or whatever. To one extent or another, we all do. But there's all kinds of probability experiments. One experiment would be randomly selecting a sample out of a population. And you might wonder what's the chances of selecting a sample that has a mean, let's say, greater than a certain value or less than a certain value, something like that. Okay, so statistics and probability are going to go hand in hand. So what we're going to do is I'm going to just use these two examples to illustrate how to calculate a probability. Okay, so now a sample space. This is another term. Okay, so all the sample space is you can think of this as the collection of all the possible outcomes of an experiment. Okay, so this would be the collection of all possible outcomes of an experiment. So, for example, like rolling a 6-sided dice. This is a very simple experiment because there's really only 6 outcomes. You could either roll a 1, a 2, a 3, a 4, a 5, or a 6. Okay, and each one is equally likely. Okay, you roll the dice, it's going to be one of those 6 numbers. So we could list them out in brackets like this. So if you've ever learned about sets, this is kind of related to sets. We're not going to do anything with sets. We don't need to know about sets. But this is the sort of notation that you use when you work with sets. Okay? So there's only 6 outcomes. Very simple sample space. So what about drawing a card from a deck? So there's actually, I'll just say the 52 cards in a deck. I'm not going to list them all out because there's a lot of them. The 52 cards in a deck of cards. So in this case, this is a sample space that has 52 outcomes. Okay? Now, I know not everybody is familiar with playing cards. So let me just explain real quick. The way that a deck of cards works is that there's 4 suits. There's the spade, club, heart, and diamond. And these 2 are like the black suits. And the heart and diamond are the red suits. And then each suit you have, each suit has 13 cards. So, and those cards are the ace through 10. So ace is like a 1. The deuce, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have like 1 through 10, but then you also have 3 face cards. Jack, queen, and king. So in other words, there's like an ace of spades, a 2 of spades, all the way up to a king of spades. And then each of these suits has the same 13 cards. It would be like ace of clubs, 2 of clubs, 3 of clubs, all the way up to king of clubs. Same with hearts, same with diamonds. And so there's 13 cards for each suit times 4 suits, and that would give you 52 cards in a deck total. Oops, I meant to circle the whole thing. 52 cards in a deck. Okay? And then you could say half of the deck is black. These 26 cards, half of it's red. These 26 cards. So you have red and black. So, and let's see. And I'm sorry if this gets a little twisted. To be perfectly straight with my desk, this is actually perfectly straight with my desk. And so somehow my camera's not quite... There, that looks pretty good. I'm just looking up at the screen. Okay, that's pretty good. Now they're both kind of straight. You also have, you have 10 face cards for each suit. I'm sorry, you have 10 number cards for each suit. So there's 42. I'm sorry. There's 40 number cards total. Ace through 10 for each suit. 40 number cards. And then each suit has 3 face cards. And that's 3 times 4. So there's 12 face cards. So there's 40 number cards, 12 face cards. Again, 52 cards in the deck. Okay? So on the homework, you'll probably see some probability problems that involve playing cards, and this will help you a little bit. But I know not everybody is familiar with playing cards. Maybe they don't play card games very much. And so on the test, I try to stay away from problems that involve playing cards. Okay? But that would be the sample space. So if you randomly select a card, it could be one of 52 cards. Okay? So now I'm going to define something called an event. Okay? And there's 2 ways to look at this. An event is, you can think of it as something you want to find the probability of. Okay. So an event is something that you want to find the probability of. Like if you roll the dice, it may be, and let's actually do these two examples. If you roll a 6-sided dice, maybe you want to find the probability of rolling an even number. That's something you could want to find the probability of. Maybe there's a new game in town that people are playing, and the game is you roll a dice, and if you get an even number, you win. Okay, I know it sounds like a silly game, but that could be a game, and in that case, you would want to know, well, what's my chances of winning? What is the probability that I'm going to win? And so rolling an even number would be the thing you would want to find the probability of. Okay? Now, what I want to do here is I want to show you that there's actually another way to think about the event. So I could call this event E. E for like even number. And event E in this case would really be just the numbers 2, 4, and 6. So it's a collection of outcomes taken from the sample space. They call this is a subset of the sample space. So you can, in a sense, think of an event as being a subset of the sample space. But again, we don't need to talk in terms of sets. What I'm wanting to show is that for anything you want to find the probability of, there's a collection of events such that if one of those outcomes occurred, then the thing you want to find the probability of, that occurs. So if I roll a 2, a 4, or a 6, if I roll any one of those, then rolling an even number occurs. So 3 of the events in the sample space are rolling an even number. Okay? So I could also do maybe something like drawing an ace. What's the probability of me drawing an ace? So there's a game. You randomly draw out a card, and let's say if it's an ace, you win. And so in that case, you want to know what's the probability of drawing an ace. Okay, so maybe I could call this event A, and then in this case, the event would be the ace of spades, the ace of clubs, the ace of hearts, and the ace of diamonds. Those are the 4 aces that are in a deck of cards. So in this event, drawing an ace, there's 4 outcomes of the experiment that would end up being this event, drawing an ace. So drawing an ace is not an outcome of the experiment. You would say that's an event. And in that event, there's actually 4 outcomes. So you really want to, when you think about the outcomes of the experiment, these are the most basic singular. They make up all the possible things that can happen. Like drawing a card from a deck, drawing an ace is not just one of the outcomes, right? Because there's 4 aces in the deck. So each individual ace is an outcome, and all 4 of those together make up the event, drawing an ace. Okay, so you got to kind of keep those separate. So the outcomes of the experiment are those single possible outcomes that could occur, and the event is something you want to find the probability of, which can contain multiple outcomes. So now with these things defined, I can now define a probability. And maybe I'll go to a new sheet to do this. So the probability of event E is given by the following definition. So what you would do is you would write inside parentheses whatever that event is. So I'll just say event E. So inside this parentheses you would, drawing a king, rolling an even number, if you've already denoted it with like A or E or whatever, you could have just probability of A, probability of E, okay? But you don't have to denote the event with capital letters. You could just write the event, whatever it is, inside the parentheses. And this is saying probability of event E, okay, it is equal to the following. It's going to be the number of outcomes in event E divided by number of outcomes in the sample space. Okay, so the bottom number is the total number of outcomes that are possible. The top number is the number of outcomes in that particular event that you're interested in finding the probability of. Okay, so for example, you could have the experiment is rolling a 6-sided die, and you want to find the probability of rolling an even number. So maybe I should say, what is the probability of rolling an even number? So what is the probability of rolling an even number? So I'm explaining what my experiment is, and I want to know what the probability of rolling an even number is. So then I could say something like probability of rolling an even number. So I could like write it in parentheses. If I've already defined it, rolling an even number, to be like event E or something, and I know that's what event E is, then I could just say P of E, okay, to simplify the notation. But in this case, if you're just finding the probability, it's okay. It's probably better to do that, because then you know for sure what you're finding the probability of. Now when I do this, what I do is I first think about the experiment, and I think, what are the total number of outcomes? So in rolling a 6-sided dice, there's 6 outcomes. And I put that bottom number down, okay, because this is all of the outcomes that are possible. Now, as I'm looking at that number, I think, out of those 6 outcomes, how many are even? Because I want to find the probability of rolling an even number. And then I think, well, 2, 4, and 6. So there's 3. 3 of those outcomes are even. So 3 over 6, and that would be the probability, 0.5. And so what is the probability of rolling an even number? It would be 0.5. Okay? And sometimes they think of these as percentages. So sometimes people might say 50% of the time. So 50% of the time you're going to roll an even number. Half of the games you play, you're expected to win. Okay? So now it doesn't matter if it's a percent or a decimal or a fraction, they all mean the same thing. But oftentimes we think of the probability as being kind of this decimal number, because as opposed to the percent, because there's going to be other formulas where you actually put in the probabilities of other things in order to find new probabilities. And so and what you put in those formulas are decimal numbers. Okay, so this is normally thought of as the probability, but oftentimes we talk about percentage of time, like this percent of the time it's going to happen. And so we think of those in terms of percentages. And basically what you can think of this as is it's the percent of outcomes in the sample space that are in the event. So half of the outcomes in the sample space are in the event. Okay? So that's actually what it is. So let's try another one here. Drawing a card from a deck. What is the probability of drawing an ace? What's the probability of drawing an ace? Okay, so I might write probability of drawing an ace. And then I'm going to put the bottom number. The bottom number is the size of the sample space. And there's 52 cards in the deck. And then I think out of those 52, how many are aces? And I know there's 4. So there's 4 out of 52. And so I take my calculator. I can do 4 divided by 52. And I get like 0.0769. So I'm going to have to round. And maybe I'll round to 4 decimal places. 0.0769. Oftentimes I round my probabilities to 4 decimal places. I think on Connect Math they might have you round them to 3 decimal places. It's up to you, okay? So, but if you do round it, you do have to say approximately equal to, okay, to know that it's not exactly equal to that. And so if I wrote this as a percent, it'd be like 7.69% of the time. Okay, so I could then tell, which one's more likely. Would I be more likely to win this game where I have to roll an even number, or this game where I have to draw an ace? And the answer is you'd be more likely to roll an even number. That's going to occur 50% of the time, while this only occurs 7.69% of the time, not even 10% of the time, right? Okay, so it forms a measure of how likely something is. And so you can think of a probability as being on a scale of 0 to 1. Okay, and this is where 0 is impossible. So if something has a probability of 0, it means it cannot occur. And 1 is certain. So this means it must occur. And then halfway between that would be like 0.5. And this would be just as likely to occur as not occur. Okay. Sometimes we would say that the odds are 1 to 1. If the probability is 0.5, then we say, the odds are 1 to 1. Meaning for every one way you can win the game, there's one way you can lose the game. Okay? And that's a kind of a slightly different language for saying the same thing. Okay? So let me give you like an example of an impossible event. If I was thinking about rolling a 6-sided dice, and I want to know what's the probability that the number is greater than 10, well, 0 of the outcomes, 0 of the 6 are greater than 10, right? So the probability is going to be 0, okay? So the way that you get a probability of 0 is that none of the outcomes are in the event. And so it doesn't matter. I could roll the dice all day long. I'm not going to get a number greater than 10. It's impossible. And so an example of a certain event would be rolling a number less than 10, right? Out of the 6 outcomes, all 6 of them are less than 10. And my probability, any number divided by itself, is 1. And so in this case, it's a certain event. It must occur. Okay? So 0.5, that's just as likely to occur as not occur. 0 is impossible. 1 is certain. And then as you go up from 0.5 up toward, this is just as likely to occur as not occur. As you travel towards 1, you become more and more likely until you hit 1, and then you're certain. And as you go down from 0.5 down towards 0, you become less likely, less and less likely until you hit 0, and then you're impossible. Okay? And then you're on that scale of 0 to 1. So your probability will always be between 0 and 1. So when you're using some of these fancy formulas where you plug in other probabilities and you get a number out that's bigger than 1, you know you've done it wrong. In these, you should not get a number bigger than 1, because there's no way the top number, there's no way the number of outcomes in your event can be more than the number of outcomes in your experiment. Okay? So, and now I want to share one last thing here before we bring this particular video to a close, and that is, if you go to the casino, none of the games are 1-to-1. None of the games have a probability of 0.5. You're never just as likely to occur as not occur. The probability that you'll win a game is always less than 0.5. Okay, and this is why a casino makes money. There's actually a theorem called the law of averages, or the law of large numbers, that say as more and more people play, the amount that they're going to make is they're going to be guaranteed to make money. Okay, so now there is one thing in the casino that's pretty close to 0.5, and that is red or black on the roulette wheel. Okay. If you bid red or black, because there's 18 red numbers, there's 18 black numbers, okay? But just so that it's not 50-50, there's also 2 green numbers, and they are 0 and 00, okay? And so what that means is, like, the probability that it's red or black, either one, okay, it's going to be, you got to add all these up. And the bottom number, there's really 38 possibilities. And for red, 18 of them are red. And so 18 divided by 38 is like around it would be approximately 0.4737 if I round to 4 decimal places. So notice that is actually less than 50%. Okay, this is in the whole casino. This is the thing that gets close to 50%. They would say that a fair game would be where you got 50. There's a 50% chance you could win, like flipping a coin or something like that. Okay, this is the one that comes closest. But what you'll notice at a casino is the bids that are closer to 50% don't pay out as much. So if you do win this bid, you really don't make as much money. And then the less likely they are, the larger the payoff. But the more risky it is, the less chance that you'll win. And that's how casinos operate, and that's how they make their money. And there is actually math that shows that they are guaranteed to make money. Okay? So in the next video, we're going to actually look at some basic rules to help you find different probabilities.